Hello guys, welcome to episode 3 HaskellRank, where I solve HaskellRank problems using Haskell. So today I'm going to attempt to solve a slightly more difficult problem. It's rated medium. Hopefully I can still solve this in reasonable amount of time. If it goes too long, obviously I'll probably skip not upload it. Let's get right into it. Okay, so we can first just create the snippet. So let's read the problem. So David has several containers, each with a number of balls in it. He has just enough containers to sort each type of ball he has into its own container. Okay. David wants to sort the balls using his sort method. As an example, David has n equals 2 containers and 2 different types of balls, both of which are numbered 0 to n minus 1. Okay, both of which. Okay. And the distribution of ball types per container are described by an n matrix. Okay. For example, consider the following matrix n1, 4, 2, 3. So the first row it represents the data for the first container, the second row for the second container, and it's divided by the type of balls. So 1, 4, meaning you can say there's quantity 1 type of ball and quantity 4 of the other type of ball, and then the other container contains 2, 3. Okay. In a single operation, we can swap 2 balls located in different containers. Okay. Now the goal obviously is to get them get each ball into its own container, which means container 0 should have only balls of 0 type, and 1 should have only balls of 1 type, ball 1 type, and so on. Okay. Thinking about this problem with just 2 containers, it's straightforward. As soon as you add at least a third container, it should get a little bit tricky, I think. Okay, let's just first read the problem. Let me not. Yeah. So in a single operation, David can swap 2 balls. Yeah, that's fine. The diagram depicts a swap operation. It's fine. So the one thing that I noticed here already is the fact that in this specific example that they have given, so essentially each row defines how many balls there are in that specific container, right? And so what I see is, for instance, container 0 has 1 plus 4, essentially 5 balls, right? That's the capacity essentially. And if that is the case, what I also notice is that when you look at the quantity of type 0 balls, there are only 1 plus 2, 3 type 0 balls, which automatically implies that it's not actually possible to actually get the desired result, which is getting all balls of one type in one container and the other in the other, because the quantity of balls we have of one type is lesser than the capacity of the container, which means there'll always be other balls in the container which are not of the same type. So it's definitely not possible. And for each container contains only balls of, so that's the goal, right? Each container contains only balls of the same type. No two balls of the same type are located in different containers, right? Essentially the same thing. So you must perform Q queries where each query is in the form of a matrix M. For each query, print possible on a new line if David can satisfy the conditions above for the given matrix, otherwise print impossible. Okay, so for a 2 by 2 matrix, this feels like it boils down to the whole count thing, right? But then even if we have like a 3 by 3 matrix, now let's just think about a 3 by 3 matrix again. All you have to do is match the counts of the type of balls, because only as long as we have the adequate counts of balls, there is a possibility. If the counts do not match the capacity of containers, then it's definitely not possible. Now, whether the fact that the counts do match, is it still possible or not, I'm not 100% sure offhand. Logically, it should be possible always, but we'll see. I'm going to go with the approach that I described. I'm going to go with a very simple mathematical approach that will just basically try to come up with a match where we essentially will match the sums of the rows, which is, I would call it the capacity of containers, with the sums of columns, which is the count of each type of balls, right? As long as those match, we are good, which means we can probably make use of transpose function, and that way it that way we might be able to simplify the whole operation. So let's see. Let's start with the sort of the input parsing. So before we try to understand what the input represents, so it says the first line contains an integer q, which is the number of queries, and then each of the next q sets of lines is as follows. One, the first line contains an integer n, which represents the size of the matrix, right? The number of rows and balls types, which is the same. I mean, yeah, it's supposed to be the same. Each of the n lines contain n space separated integers describing row m of I. Okay. The first thing first, like most of the other problems, we can definitely ignore the first number because we just recursively solve all test cases without worrying about how many test cases there are. This works because we process the entire input uh, in one shot. So the first thing is n, and then the rest of it, let's call it ns, right? But let me call it nss because it actually represents everything remaining, right? It's not just the matrix. So I mean, we will see. So we say where I would call it, let's say ns, yeah, is equals to take n from nss, and then rs meaning the remaining stuff, which is drop n from nss, right? So our answer would look something like, so we have to first solve for uh, the first test case and then recursively solve for the remaining test cases. right? So the one thing I see is the fact that RS, it's may be null, right? Like towards the end, when we reach the essentially when we reach the last test case, the um, remaining input data would obviously be null now, or an empty list. And so null is a check on list, which uh, null is a check on list which tells us that the list is empty. So when the list is empty, we have to essentially give the output of, let's define is let's call it it's sort possible, which essentially takes um, again I think the number n itself is not really relevant. We can do a computation without having that, and so this will give me a boolean, right? This will give me a boolean. Okay, and so what we will say, or we can actually go ahead and say this is just a boolean, right? So okay, right. Based on the boolean value, we have to essentially convert this boolean. So let's do this. So we'll have to let's let this be the string representing whether it's possible or impossible. Okay, given that is the case, we will obviously be returning multiple strings. So when it is null, it'll just be possible to have this thing. Let me say, so this will be like let me just inline it. So is not possible ns. Yeah, because for the most part, oh no, n is required for the recursive parsing, so we'll keep that. But our function is not possible really doesn't care or need n. And so this guy now will be in fact, so is not possible ns and then solve. Yeah. Yeah. So now we just have to basically figure out the validation part. Okay, I'm still a little bit okay. We'll see where exactly we translate the boolean into a string representing possible or not. So, like I said, the logic that at least I came up with, I don't know yet if my logic is correct, but it does sound correct. That all we have to do is match the sum of the rows with the columns. So essentially, the sum of the rows must match sum of the rows in the transpose matrix. Sorry. So for transpose, we can just import Data.List. Data.List has the transpose method. It's a bit too long, but it's okay. So it does have the transpose method, which we just have a look at in a bit. It's odd. It's taking too long. Okay. Yeah. So yeah, so let's look at the doc for transpose. I mean, I think we all should be aware of what transpose does. really straightforward. It just transposes the matrix. It is, I think, fairly easy to do it yourself, but then since there is a library function available, why not make use of it? And like I said, so what we have to do is we have to match all of the right. So we have let's call this ns, and then I will say where ts is equal to transpose of ns. Okay, and now like I said, so we can, for instance, this as a for demonstration, right? We can map sum over ns, and that gives us the sum of each row, and we potentially want to equate this with the right. So let's call it sum ns becomes map sum ns, and then sum ts becomes map sum ts. I guess it is possible to do this without transposing also. And how you would do that is, yeah, I think it's easier to just use transpose and do it. But we'll see. What's the ns is not an int. What? There must be a mistake. Expected. Oh, right. Mm-hmm. Oh, yes. So, yeah, what is happening is because of the way we are passing the input, what is happening is, so we get essentially two. So when you look at this guy, right, line number 11, so when we say is not possible of ns, what we really get, ns it would actually have this entire matrix, but as a one-dimensional array rather than a double array. We obviously want a double array. What's the best way to do a double array is to build one chop function, so which will take an int, an array of int, and it will return a two-dimensional int. So let's say chop of n becomes something, where let's say, oh yeah, so essentially what we'll do is right, so we take n from ns. So what I'm trying to do is I'll say that n is essentially the size of the uh, the 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 width, or the number of rows or the number of columns. In this case, it's the square matrix, so we don't distinguish. So yeah, so what I want to do is, given a one-dimensional array, I want to chop it down into a multi-dimensional array where each row would be of size n, right? So what that gives me is that, so if we first take the n elements from array, and then remaining would obviously be drop n ns. So this would then become yeah, so we take fs and then we just cons it with chop n of rs. That should do it actually, right? This should do it. And so what we can do here is we can say cs, which is chop of chop of n of ns, right? And I will now also pass n. It turns out we will need it, right? Let's do this. So we chop the thing by this thing, and then now we should be good. Yep, and now we should be good. Obviously, it remains to see uh, what I want to do now. Now we have SNS. Now SNS would so CS, which is the chopped thing. Let's first test the chop function. Okay, so we'll say chop 2 1 1 1 1. That's the first test case. Oops. Yeah, so that's not ending, and that's probably because if it's empty, it should be empty, right? Cool. Yeah, that's cool. Let's, for the sake of argument, let's try it on 1 1 1 1 1 1 1, and that's, yeah, that gives you a two-dimensional 3 by 3 matrix. So the job function does its job. Now what we want to look at is sort possible. I want to no, what I want to look at is what does. So let's say ns is chop 2 1 1 1 1, right? So this becomes a two-dimensional array here. Now we will map sum through ns, right? And as you can see, it becomes a one-dimensional array where each value is the sum of the entire row, right? And when you, I mean, in this case, because it's equivalent, right? It's a one by it's the same matrix. So transposing gives you the same matrix. Let's look at maybe NSS chop to 0 to 1 1, right? So this is slightly different. So NS looks like this, and transpose of NS will look like this. And so if you look at map sum of NS, and also when you look at map sum of transpose of NS, this is what they look like, and they don't match, obviously. So for the purpose of matching, I think what I will do is I'll make use of since all of them must match, we'll make use of all. All is the nice little yeah, so like it says here, so it determines whether all elements of the structure satisfy the predicate. So if you look at the type of OR, so it takes a predicate which maps the individual value to a Boolean thing. It's a function which will determine essentially whether based on certain criteria, it will determine whether your criteria, whether the data point satisfy the criteria or not, and it applies it on each and every element of your list. We have to see. Oh, yeah, it'll apply it on each and every element of your list, and the expectation by seeing all is the fact that all of the elements of the list must satisfy the criteria, otherwise it fails. Even if one doesn't satisfy, the result of all will be false. But in this case we have two lists, so I think we can just say there should be a way to, we can always use something like zip. We could zip so we could zip the two arrays. We'll get a tuple, and then we can do a match on, let's try that maybe. So zip of SMS and STS. I don't know if there's a better way. Also, what I want to look at is we had this NS, so we have map sum NS, right? And then we have map sum of NS. Let's say SNS is this. Let's say STS equals to map sum transpose of NS. Now I was trying to utilize all and shit, but like I'm I'm thinking that just doing this should work. So in this case, it obviously says false, but if, let's say, if it were this returns true. Okay, so then in that case, I can actually literally just equate them. I can just say, oh no, since we have to return a string, so let me say if SNS is equals to SDS, we will return true. Otherwise it's impossible. Let me just confirm the case. Yeah, and that should be it. At least on the basis of a very simplistic algorithm that I've come up with. We may have to see if this is foolproof. I'm not entirely sure if it is. Also, we don't know yet if this is fast enough. So it says impossible, possible, impossible, possible. This is weird. This is very weird. We have only 2 test cases. I would expect 2 outputs. This is confusing. Oh. We have to take n plus 1 from this, and we have to drop n plus 1. That's because that's because we include the number n itself along with the matrix, which is n by n, right? Oh no, in fact it's not even n plus 1, so we have 2, which represents the number of rows, right? So which means the size of the matrix would actually be 2 star 2. So n star n. Yeah, this makes sense. So this way, plus 1 is because we have to also include the number n itself. Yeah, I think this should be fine. Let's see. We still have to improve our output, but yeah, we'll get to that. It's taking a while, which is odd. In the meanwhile, let's just improve our this thing. So instead of show, we'll use unlines. I think that's it. Wow, why is it taking so long? It's because OBS is eating up my system, I think. But let's see. What the hell? Why should the compilation take so long? That doesn't make sense. Try once again. Why should the compilation take so long? It says impossible. Impossible. Yeah, I think we have to double check. So I say tail, so that removes the first, and then I say n double s, right? And so for ns, yeah, I've already extracted n, haven't I? The system is slow. I've already extracted n. I don't need the plus 1, right? So we have n, and then we need to take n star n, I think. And then yeah, okay, yeah. So it says possible, and then the second is impossible, which matches the example use case. Unfortunately, they've not given us a slightly more complex test case. So I'm not entirely sure if my logic is 100% correct. It's definitely close, if not. We'll see. We'll see. Let's try it out. So obviously, should pass the test, uh, the sample tests. But yeah, just yeah. So that's fine. Let's look at how it does on slightly bigger input bombs. Wrong answer. Oh, that's sad. So there is definitely something missing in my logic. Just the just by matching the counts, just by matching the counts is probably not enough. Right, the capacity of the first guy must match the number of zero, the first type of bond, right? I think the matching should definitely be, or rather, the fact that if it doesn't matches, then it's impossible. But like I said before, when it does match, when it when it does match, even then, I don't think we can guarantee. I don't think we can guarantee that it's possible. Let's see. I think I'm gonna get the test case and we'll look at exactly how our solution behaves for this test case. As you can see, it's pretty big. Okay, so we have 10 test cases here. Let me just first just try it out and see what the output is. So possible, and then all of the remaining are impossible according to my solution. However, we are clearly wrong. So even for the second one, for instance, it says this guy. It says that it is possible, but why? But my solution says it's not possible. It's impossible, which implies that the it's weird though, right? What are these numbers? Wait. Oh, so the okay. Let's look at so it says let's try and utilize the debug.trace. And so I'll say, oops, I'll say trace, and we will try to trace show SMS plus plus, let's say let's do this, and we'll say STS, show STS. Let's look at what it shows, what the sum stuff look like. So SNS looks like this, and what I'm noticing is uh-huh. Oh, that's interesting. That's a little bit interesting, but I get the point. I think yeah, I get the point. Essentially, it just means that assuming the order is probably wrong. So there are a few things I can do. I can either compare, I can sort them and compare them, right? But I'd have to sort both of them. Or instead I could utilize the this function, the list difference function, which in this case implies that it essentially would be empty. I think so. Now it should definitely say possible because it's just that the order was different. It does make sense, right? I mean, so I'm trying to match 0 with 0, but it doesn't have to be. It doesn't have to be. You know, as long as one matches at least one of them, it's fine. Why should it be? Yeah. So now that we have this, sorry. So yeah, I think I still don't know if this is fast enough though, but let's try this. So I'll just, yeah, let's test it out on our sample test cases. Once again, just to make sure this is not something very obvious that I missed, but let's see. Cool. Hmm. This was, unfortunately, this was much simpler than I expected it to be, considering that it's a medium. Honestly, I expected it to be much simpler, much more difficult, sorry, so that we would have been able to see some more complex Haskell code, maybe even using data structures and stuff. But I guess it would have to be for now. I mean, I can't see any major improvement that can be done, neither in terms of complexity nor in terms of like improving the readability. There's something we can do. Again, like very, very minor stuff. Nothing major. Not fast enough, actually. Okay. So HaskellRank. Oh, cool. There you have it. 28 lines of code. Very readable, very functional.